Guys, in the last video, we were talking about formal charge. And when we talked about formal charge, we said that it was a shortcut to help us draw these structures in organic chemistry a little bit quicker. So here are the rules. If you have hydrogen, that really can only get one bond. If you have carbon, that normally always will have 4 bonds. If you have oxygen, it's always 2 bonds with 2 sets of electrons. If you have a halogen, it's 1 bond with 3 sets of electrons. And if you have something like nitrogen, it's typically 3 bonds with 1 set of electrons. If you can remember those rules, then maybe you can piece together this information a little bit faster than someone who has to go to the very basics of a Lewis dot structure and draw these things from scratch, starting with the valence shell electron count. All right? So I told you that in the last video, there's actually carbons that have no formal charge. But there could be carbons with a charge up here at the very top. And I told you that this is something that we're going to be seeing quite a bit throughout the semester. So we might as well go ahead and put it out on the table, allow you to look at it, allow you to absorb it, allow you to understand it and feel comfortable with it before we get to the nitty-gritty later on in the weeks to come. And this is a positively charged carbon and a negatively charged carbon. So normally carbon wants 4 bonds, 1, 2, 3, 4. And if it has 4 bonds, the charge is 0. However, carbon could end up getting 3 bonds. Well, carbon normally has 4 valence, minus 1 from each line. This gives me a positive 1. So basically what that means is that he's short a bond. This can happen in organic, and it can happen in organic reactions. It doesn't stay around very long, but it can happen. So anytime we see the charges like this, what we've discussed before in the previous videos is that this is an ion. It is a charged atom. Okay, well, what type of ion is it? Well, it's a cation because it's positively charged. Well, we have a term that's called a carbo cation. And carbo cation basically means a positively charged carbon. And this is what we're going to be referring to. So, again, later on in the weeks to come, we will be talking about carbocations. We will be mentioning them. We'll be drawing them. We'll show you how they rearrange and how they behave. And this is the basic staple of that. Well, if you can have a positive version, you can have a negative version too, folks. And if you do, well, this is going to be called a carbo anion. Right? Go figure. Anion means negatively charged, and this is a negatively charged carbon. So carbo anion. Carbo anions we'll discuss. They're not as common this semester for us. We won't see them very often, but they are out there. So I'm not going to give you a full-blown description right now, but I'm going to put this out as a possible choice. If you have a positive version, you can also have a negative version. One's called carbocation, one's called carbo anion. The carbocation is going to be the most common for us as we go throughout this course, and that is a carbon with 3 bonds instead of 4. That's all that I really want to say about carbocation at this point. Okay, so there you go. There's just some definitions and some common terms that can come along with it. Now, I do want to take a few minutes and I want to talk about carbon. And I'm going to go back and I'm going to draw the electron configuration. So 1s2, 2s2, 2p2. Okay, so there's electron configuration for the normal carbon. If I add up all of the superscripts, I get a total of 6. And then if I look at the last orbit, orbit 2, we're going to see 2 from the first shell and then 2 from the p shell. So this is a total of 4. 4 valence, so it all matches. Well, we also said that we could show all of the principal blah, blah, blah rules, right? So 1s2 has 2 arrows, 2s2 has 2 arrows, the p's have degenerate orbitals, and there's 1 and there's 2. The reason that I'm doing this is I'm getting ready to set up an argument here. And the argument is I just told you that carbon has 4 bonds, right? And with each one of these bonds here, we said that these always represented 2 electrons, okay? So if I take a look at the way that this carbon is structured, it looks like there are 4 bonds, which means 4 sharing bonds. Okay, well, if I look at the electron configuration, folks, this very first box is doubled. It's already paired up. Therefore, we would assume that this box is a no-go. It's already paired up. There's nothing else that can go there. And then if we look at this box, it's also paired up. So this one's a no-go. And it looks like we only have 2 electrons that are unpaired. 2 electrons that can participate in bonding. That's how this electron configuration looks. Well, if there's only 2 electrons that can participate in bonding that's available for a 2 electron pair line, then how on earth can 4 be created? This doesn't quite make any sense, does it? So, for instance, carbon, and we have 4 bonds, each one to a hydrogen. Well, each hydrogen brings with it an electron. That's its Lewis dot structure. And that carbon has 4 electrons. That's its valence. The issue, though, is that out of those 4 valence, 2 of them are unpaired. The other 2 are paired up. These are not available. Based on the electron configuration, it's not going to work. This has always been something that's very confusing for organic chemists. They don't want to admit it, but it is a problem area. How can we create 4 bonds like we've drawn here that we've accepted over the course of time? How can we get 4 bonds out of something that only has 2 electrons available to pair up with? So what did they do? They go to the drawing board and they say, well, let's fudge. So I'm going to draw the box for 2s2, and then I'll draw the 3 degenerates for P. There we go. And what organic chemists have said is they make up a theory, and they say, guess what? This will work, but it's got to work the way we want it to work. If we want carbon to participate in 4 bonds to get a formal charge like it does in example CH4, we need 4 electrons that are free to pair up and be shared. How do we do this? Well, someone said, why not we just erase this electron in this box, and why don't we draw that electron over here in this box? So we'll pretend like they're not pairing up in this first subshell, and it will go to an available other subshell, in this case a p degenerate. And they make the argument this way. Electrons are getting paired up. And as you know, an electron is a negative and another electron is a negative. These 2 things repel each other. They hate each other. They don't want to share the same room. It's like a bad brother and brother or sister and sister. They don't want to be in the vicinity of each other. So, if one of these electrons figures out that there is a bedroom in the house that is not used up, and that bedroom is empty, then they will make a decision to move their belongings into that bedroom and claim it as their own. And this is what organic chemists have basically stated over the course of time. Normal electron configuration, if we go by all of the rules and the principles that we set out to do, pairs up the 2 electrons in the 2s2 before it goes any further. However, in order to make this stuff make sense, that doesn't quite work out the same every single time. So we erase the electron that's here, and we promote it. And we promote it to an empty p orbital. Well, this is what we are going to call a hybrid. Yes, that term hybrid is coming back, but it's representing something else now. and it's hybridization theory. The reason that we call it hybridization theory is because we are involving here a s electron, and we are involving now all three of the p's. And this is an sp3 hybridized bond. That is what that refers to. So sp3 hybridization basically refers to the bond that is shared between these hydrogens and the carbon. And we say that carbon is sp3 hybridized in order to make this work. If it wasn't hybridized, these two electrons would be paired up in the 2s2 block, and there would be no availability for extra bonding for two of those hydrogens. But in order to get carbon to make the 4 bonds, we have to move this electron from the s block, and we have to move it to the p block, and all 4 of these now can participate in 4 bonds. One needs a pair here, that one can bring in an extra, this one can bring in an extra, and that one can bring in an extra. Remember, the magic number is 2. So this is what we call sp3 hybridization. And this is how carbon makes 4 bonds. If we did not bring in this hybridization rule, folks, we could not explain how carbon makes 4 bonds. There's only 2 available spots. There's only 2 electrons there that can be shared. There's only 2 electrons there that can actually be paired up with something else. So we have to hybridize it, and this is the way that we do it. All right? So this is your first lesson on a new topic, and that topic is hybridization theory in terms of organic chemistry. This is stuff that they probably did not teach you in general chemistry. And remember what I said? I said that along the way, I'm going to scatter information in that you probably have never heard of. And this is one of those tidbits of information that's new to you at this point. So sp3 hybridization is a made-up theory. This made-up theory promotes an electron to a degenerate orbital. Therefore, all 4 orbitals now in the valence shell are freed up, and all 4 of those can participate in a bond. And that allows carbon to have 4 bonds to 4 things. And in this case, they're all hydrogen. They could be different. They all could be different. It doesn't have to be all hydrogen, but it works the same way every single time. So what you're seeing in this diagram is the depiction of hybridization theory. So what they've done over here to the left-hand side, they have showed the promotion already. So the S did have 2, but now they actually transfer that over to that third P, and notice it says 4 orbitals are now hybridized. So the way that they do that is that they rewrite it. The reason they rewrite it is because it's not truly an S, which is spherical, and it's not truly a figure 8 shape, which is the traditional P. It is a hybridized model of those 2 systems together. And this is what you're going to see down here at the very bottom. You do see that figure 8 that's there, but it's not equal. One lobe is a little bit bigger than the other lobe, and that's because of the presence of the s orbital that is present. It changes the shape of a traditional P figure 8. So we'll rewrite that, and they rewrite it as sp3s for each one of them, because it is a mixture of the S and the P's that are present, and this is how carbon gets 4 bonds in total. So the depictions at the bottom show you that it does have an effect on the actual orbital shapes that these things begin to take on. And this is very traditional. In organic chemistry, when we start talking about shapes, we're always going to have more exceptions than we are rules, it seems like. And this is one of those things, okay? Carbon promotes. Carbon frees up an electron, 2 of them actually, in order to pair those 4 singles up to a partner. And now there's 4 couples that are at play. And that is what we call the sp3 model as we come along. Okay, so that's the depiction in the textbook. If you're reading about hybridization in the textbook, this is what they are referring to. And hopefully now when you go through some of that wording, you're not completely lost, because that's what it means. That's what they're talking about. Here's another depiction, this time of ethane. And ethane is a CH3 molecule and a CH3 molecule. So this is how we would normally draw it if we want to represent three-dimensional structure. Your ball and stick model is represented, your space-filling orbitals represented, and your electropotential or static potential map is also represented. Down here at the bottom, though, is another representation of ethane. And what they're showing is that these hydrogens will have the S's typically, and there they are. That's why they're drawing them as spheres. And then the carbons typically are going to be these lobes, these p lobes, right? So we know hybridization is going to exist, and when hybridization happens, this is a sp3, this is an sp3, this is an sp3, this is an sp3, so all four carbon bonds are the same, and then we go around clockwise like that too with that carbon. So we have sp3 here, and sp3 there, and sp3 here, and sp3 here. So there's our hybridized model. So whenever we talk about the carbon to hydrogen bond, we are talking about a sp3 and a S overlap. And the reason that the S is there is because that's what hydrogen has going for it, right? Hydrogen is 1s1. That's all that it is. There's no P's involved at all. It is strictly a spherical shape. It is a S subshell. Well, carbon had to promote. Carbon had to hybridize. So therefore, the bond that carbon now has is a sp3 bond. So we say this is a sp3 and S. If you write this backward, it's okay. It means the same thing. S and sp3, no difference in sp3 and S. If you want to write it backward, fine with me, no big deal. The only one that's different is this carbon to carbon bond. And if you look at the carbon-carbon bond, this carbon, that bond, like all the other ones, are sp3. And this carbon, like all the other bonds that it has, is a sp3. So this carbon to carbon bond is actually a sp3 to sp3 bond. That is how we designate that. So if you see these types of questions on an assignment, if you see these types of questions in a test, that is what they are referring to. So the idea, carbon hybridizes, the idea that it frees up 4 electrons that are all single, and the idea that all 4 of them now are going to go out and look for a partner. That is a sp3 hybridized orbit in every single case. So whatever decides to come into the picture, as in the case of hydrogen, it brings with it its orbit, and we can designate the type of bond that that's going to be by looking at orbital notation. Now, this is just the beginning of a conversation. I know that this is new information. I know that I went through that pretty quickly, but we're going to see more examples of it, and you're going to understand that this is not complicated, okay? This is going to be a very quick glance at a molecule for you, and you will be able to determine what is sp3 and what is not. So just give me some time, and you'll learn some of those extra details in the next video. So this is just the beginning of a discussion right now. So don't let me lose you. Come back. We'll pick up from here, and we'll continue on with the discussion of hybridization theory.